Next question, question number 6, and this is a typical YDC setup here. But there's one difference in YDSE setup. Of course, rays are incident perpendicular to the slits, but not monochromatic. What is the light source used is white light. So it has several wavelengths here. Unlike single wavelength, several wavelengths are present here. So let's understand what happens in case of several wavelength. We know those who understand several wavelength here. So if, in case of several wavelength, we will not see a kind of distinct fringe pattern as we see in case of single wavelength monochromatic light. So because different wavelengths will have constructive interference at different points, so it will give, you will see different colors here. So which point we see red color, the point where constructive interference takes place. For red wavelength, we see the red color will be more dominant. It will have reddish tinge, and depending on which color is having constructive interference at a particular point, that color fringe pattern would be seen, kind of thing. So we'll see a kind of all colors here, except for the central bright fringe. Central bright fringe will see white color, basically because all rays undergo constructive interference. So this would be like a normal white light. But let's understand, the question is something else. The screen is at a distance. The first thing what you notice here, the notation used are different. So for slit width is a small b, and for distance from this distance of screen is small d. So okay, it doesn't matter. We know what is the what does the this notation stand for. What is given here? Some wavelengths are missing exactly in front of one slit. Let's take the slit 1 S1, and we take a point P exactly opposite to slit S1. It means Y will be equal to B by 2. That means it exactly opposite to the slit. At this point, we find if we check which are the wavelengths present, we find some wavelengths are missing. So whatever wavelengths are started from here, some wavelengths are not present here. What does this missing wavelength business mean? All those wavelengths which undergo destructive interference at this point, those are not present. They will cancel out. So missing wavelength imply destructive interference. So wavelengths are missing, which satisfy the condition for destructive interference. And condition for destructive interference is path length has to be equal to odd multiple of lambda by 2. So this is a condition, 2n minus 1 lambda by 2. So all wavelengths which satisfy this condition will be missing in a sense. All we need to do, we need to find the path difference at the point P, where y is equal to b by 2. So y is small here and all conditions are met. I can use this approximation. We can use path difference is equal to d sine theta dy by d. We put b is equal to y is equal to b by 2 here. So and in case of capital D, we put a small d here. So path difference is equal to b square by 2d, and we equate it to this term here. So all these wavelengths here, if I substitute different value of as in real number, we get different values of lambda. So variation of this question could be, suppose the question is which are the two longest wavelengths which are missing. Numerous wavelengths are missing, but which are the two longest one? So these are the missing wavelengths, and here we substitute smallest value of n, starting value of smallest value of n of course is 0. So the longest wavelength which is missing is equal to b square by d. Second longest n is equal to n is equal to first we substituted n is equal to n is equal to 1, corresponding to n is equal to 1 is this, n is equal to 2, we get this number. Okay, so one by one we can find out which are the wavelengths which are missing depending on which one is required. We can find the longest one, the second longest one, and third longest one, and so on and so forth. So this is a condition on missing wavelength at a particular point on the screen when all wavelengths are present in the incoming incident radiation.